Alright, so let's do a quick roll call and we'll get started. So we have Dave, Dhanushri, Praneeth, Chris, both the Chris, Neil, Saras, Nikhil and Sunarka. So did you guys get a chance to see what are the things that we're going to learn today? So we'll talk about congruence and similarity concepts, and then we will look at angle relationships. So this is the plan for today. Let's see how much we are able to cover, and then if there is anything that is still missing, we will talk about it. We'll talk about that tomorrow, or if you are able to cover all the things that is planned for today, then we'll see if we have time to cover more. So we'll start with congruence and similarity. So first of all, a question to you guys. I know you all would know it, but still, just for being on the same page, wanted to know what is your understanding of congruence and what is the difference between congruence and similarity? Yes, Nikhil.
I think congruence is like the same of sides, like the same length and the same like parallel of the two sides.
Okay. What is your understanding, Praneeth?
Congruence is when two shapes are exact replicas of each other.
Exact representation. Okay. Any other definition? In terms of mathematical way of representation, or anything that you can think of with respect to physically relating to something in congruence world. Okay, so let me not give you guys a lot of riddle to solve. When you say congruence, in the simplest form, it means exactly the same. So if I say one triangle is congruent with another triangle, if I say one triangle is congruent with another triangle, what I mean by that is these two triangles have each and every property matching. Meaning, if this is, let's say, one side, there will be exactly one matching side on the other side. If this is second side, there will be exactly one side on this triangle matching with this one. This is the third side, there will be exactly one matching side on this one. If this is one angle, there will be another triangle will have one matching angle. Same thing for the second one, same thing for the third one. So, and then that would mean these are exact replica of each other, meaning the area of the triangles will be the same. Every other property that you can think of will be same. The perimeter would be same. So basically, when you say congruence, you're talking about two things matching exactly with each other. At no point in time, regardless of if somebody is giving you $1 million or $10 million, these two will not be congruent. Okay? A triangle can never ever be congruent with a quadrilateral. Okay? This part is okay? Now let's look at other concept which is called similarity. So, and congruence could be true for any type of shape. It could be for triangle. If I'm talking about triangle, it can be congruent with another triangle when they are exact copy of each other. Okay? If you're talking about a quadrilateral, two quadrilaterals will be congruent if they have exactly same properties, same area, same perimeter, same matching angles. Okay? So that is what we mean by congruence. So in the simplest form, congruence is nothing but a copy of one shape is congruent with another one if they are copy of each other. Okay? So Sarah and I can never be congruent. Okay? Sarah has a lot of hair, I have no hair. Correct? Or very little hair. So that is one a very, what do you call, lame example of congruence or non-congruence rather. There is another concept called similarity. What do you mean by similarity? Yes, Pranit.
Similar shapes are shapes that have the same angles, but their sides are not the exact same length.
Okay. Nikhil, what is your definition of similarity? What is your understanding of similarity?
I think it's like two shapes, but they are not necessarily the same length. They could be like the same angles and the same like shape, but they're not necessarily the same like parameters, like everything.
Okay. So except Pranit and Nikhil, can somebody give me one of the most commonly used practical example of similarity? No, except Nikhil and Pranit. I want to see if anybody is falling asleep because of me. Anybody else? Yeah, Chris. No, I'm saying what is the most practical example of similarity that you can share in this group? Something that you deal with every day. Any guesses? And you guys will say, okay, I'll give you a chance, Nikhil. I'm just trying to see if I'm getting a response from anybody else in the class as well. Dave, Chris, Sanarka, Neil, Sarah, Sharon. Anybody? I'm saying one of the most classic example, one of the most practical example of similarity that you deal with every day. You as in all of us. Don't tell me that anybody in the class, there's even one person in the class who has not used phone. When you zoom in, zoom out of a picture, that is similarity. Okay? This is my triangle. If I have this shape in my phone. If I zoom in, becomes big. If I zoom out, becomes small. This is a classic example of similarity. What do you see here? They look similar shapes. This is triangle. No matter how much you zoom in or zoom out, this will keep looking like a triangle. And the angles will remain the same. This angle and this angle and this angle are same. This angle and this angle are same. This angle will be same. Okay? So the angles don't change. What has changed? The length. When you zoomed in, the length kept on becoming bigger. When you zoomed out, length became smaller. What did not change was the angle. Yeah? So this is one of the basic difference between similarity and congruence. Is that okay understanding so far? Everybody? Okay. Now let's go on to do double click on these properties. Now, when you talk about congruence, mostly we deal quite a lot with respect to congruence of congruence of triangles. Okay, and there are 4 theorems around that. They are called SSS, SAS, ASA, RHS. These are the 4 theorems of congruence. This says that if you have 2 triangles, if the 3 sides are matching, meaning I have 2 triangles where we found, okay, this side and this side are matching, this side and this side are matching, this side and this side are matching, then this applies side, side, side. Meaning all the 3, if the 2 triangles have 3 sides matching, then they are congruent. Meaning after that you can assume that the 3 angles will also match and everything else will match. Now you will say that just because this old man is telling you guys that this is a theorem, how can I believe that? And you don't have a choice. If you have, let's say, 3 sides as 4, 5 and 8, or 4 centimeter, 5 centimeter, 8 centimeters, the length of 3 sides. You can only build triangles which will be congruent. You cannot ever make a triangle, taking these dimensions, which will look different. This and this are not congruent, right? They don't look congruent. So what I'm saying is, if you have three sides known, if you use those three sides and draw a triangle, your triangles will be congruent no matter which side you are picking as base and then building those, versus picking big side as a base and then building those. How you will do it? You guys know, right? You can use, let's say if you have to draw a triangle, let's say you pick this as a base, 8 centimeters as a base. If you pick 8 centimeters as a base and the other two sides are 4 and 5, what you will do is, you take you call it compass, right? The where you hook one pencil on one side, yeah. So make a radius of 4 centimeters. Cut this from this point. Take a radius of 5 centimeters and see wherever this is intersecting. This is your one triangle and this is your second triangle. Now you can say, okay, I'll take this as a base and then one side 8 centimeter, other side 4 centimeter, and see where it's meeting. Only thing that will change for you is, you will see that, okay, this triangle is rotating, but you will end up having two triangles which are exactly congruent. You cannot change their shape, you cannot change their angles, you cannot change their area. This is something that you don't have to prove, but you can always relate to this by a practical example. You cannot draw two triangles with the same dimension, one looks like this and another one looks like this. You cannot do that. You can rotate it. If this rotate it, this becomes your base and these two become the side. If you further rotate it, this becomes your base, these two become your side on the top. But then you'll just be rotating that triangle. They will have the same matching properties, they will have the same area and every other thing that you can think of. Is it making sense, or you are still struggling to believe what I'm saying? Dhanushri, Sarah, Neil, Rehan, Nikhil? Okay. Everybody is okay to believe this? Sriyan, sorry. Okay. Now, so this theorem we are not trying to prove. Okay. Now let's look at what does the second one say. SAS. That means this theorem says, if you have two triangles where two sides and the angle between them are matching, then they'll be congruent, meaning they are exactly the same triangles. Let's look at it. You have one side, let's say, and then you have another side, and this is the angle between them. So this is your third side, okay? So this is your one side, this other side, and they are making a certain angle, and this is the line segment which is joining the two endpoints of these two lines, which is making this angle. Now, what this theorem says is, if you have two sides with a matching length, so this matching with this and this matching with this, and the angle between them matching with each other, then these two triangles will be congruent. Now think about it. If you have two sides, let's say this is 5 centimeter and this is 4 centimeter, okay? Let's say this is 20-degree angle. Then this is the length of the third side. This is one same 5 centimeter. This is same 4 centimeter. Here the angle is, let's say, 50 degrees. Okay. Now see, the length of this third side has changed. If you make this as 90 degree, so this remains 5 centimeter, this remains 4 centimeter. My drawing skill is not that great. I'm not probably making it same length sides, but just pictorially or intuitively what you see here on the board. See, when my angle is small, this side which is joining these two endpoints is smaller. When my angle increased, this side increased. When an angle further increased, the distance between the two endpoints again increased further. So what it means is, this side's length is a function of how big the angle is, even if these two sides are remaining the same, right? So if your angle is, let's say, if I'm talking about two scenarios, okay, here the angle is 50 degree, here also angle is 50 degree, this is 5 centimeter. I mean, I'm just taking an example of 5 centimeter, 4 centimeter, just to practically make more sense. But if my angle is same and these two sides which is making this angle is same, by no means this length would be different. So this length and this length would always be same, because that's what we saw, that when the angle is changing, the side is changing. If the angle is not changing, the distance between the two endpoints can never change. Correct? Is it sounding okay or it's not? Yeah? Dhanushri, you have been quiet, beta? All okay? I mean, is it making sense so far?
Yes, sir.
Okay. Dave, are you okay with whatever I said?
Yes, sir.
Okay. So net, by looking at this example, we see that, okay, if my two sides are fixed length and the angle is changing, the third side which is joining the two endpoints is changing. So that means if I am not changing the angle and the sides are same length, then these two sides will be of same length. And then while looking at this theorem, we saw that, okay, if my two sides are matching, and the angle is matching, the third side has to match. No choice. That means it became a SSS scenario. SSS scenario. So SAS is equal, is matching with this scenario already. That if my two sides and angle are matching, my third side has to match. There is no choice. That means it is same like this one. And in the beginning we saw that, okay, if I have three known sides, I can make only one type of triangle, and even if I make 5 triangles, they all will be congruent. So this is also relating to this one. My third side is also matching. So then I can assume that, okay, SAS is in turn relating to this one. That means if this is to be believed, then this one also can be believed. Is it making sense? Okay. Alright. Sarah, okay with that?
Yes, sir.
Chris, both the Chris, you guys okay?
Yes, sir.
Okay, as in, I know you guys are always okay. I mean, I'm saying you're okay with whatever I have mentioned here on the board. Yeah?
Yes, sir.
Okay, so we saw two theorems that we can believe and digest. Again, you guys don't have to prove it, but why I'm proving it, because if you know the root of this theorem, then it stays here. You don't have to memorize it. Right? Now let's look at the third scenario, ASA. Meaning, I have two triangles where the side is matching. Sorry, this is one side. A stands for angle, S stands for side. So here we saw 3 sides matching, they are congruent. Here we saw 2 sides and the angle between them matching, they are congruent. This is the third scenario where we are talking about 2 angles matching and the side between them matching. So this is the side between the 2 angles, and this is one angle, this is another angle. This is one angle, this is another angle. So these 2 angles are matching. So this is 1, let's say this is 1. If this is 2, this is also 2. And this side are matching. So we are saying that if these 2 angles are matching and the side between the 2 angles are matching, then this is congruent. Now look at it this way. Now if these 2 angles are matching, then third angle has to match any which way, right? Because there cannot be any triangle where some of your angles will be anything different from 180 degree. So this is anyways matching. So all the 3 angles are matching. Now we see that one side is matching. If we find that these 2 sides are also going to match, then we can relate to this guy and we can believe this. Or now if we find, see, we have 3 angles matching already. If we find any of the side is matching, let's say if you find that this and this are matching, then we can assume that this relates to this guy, meaning two sides and the angle between them, and we'll be fine. Then we can believe this theorem is also right. Now, think little different here. What you are seeing is you have these two angles matching on the side. So we are trying to figure out if this length and this length can be different. Let's assume that these two are not same. Meaning let's pick up. Let me draw a little clearer picture so that you guys can relate it a little better. Let's say I have these two sides matching. Let's say this is 5 centimeter and this is also 5 centimeter, and this angle is 40 degree. This angle is 40 degree. This angle is, let's say, 60 degree. So this angle is also 60 degree. So we know that these two angles are matching and the side between them is matching. Now let's assume that okay, angles are matching, but this side and this side are not matching. Okay? We are saying that these two angles are matching, but this side and this side are not matching. Let's say if this is A, B, C, this is D, E, F. What we are saying is the angles are matching fine. This BC and EF are matching 5 centimeter each. But we are saying that okay, AB is not equal to DE. Okay? Meaning we are saying that probably there is a point here. Let's say this point is K, where AB is equal to EK. Is that okay? I'm saying that these two sides are not matching, okay? So we are saying that okay, fine. Probably this distance DE is bigger than this one. That means somewhere in the middle, this angle, this length here to here is same as this guy. Okay? Now what would that mean? If I join these two, if I join these two, then this side and this side will match, meaning now we are looking at two triangles, A, B, C, and triangle E, K, F, the smaller one. Okay, basically after removing the green part of this triangle, okay, because we said that this length is, the whole length B is bigger than this one. This is not matching with this guy. So we said okay, fine, there is a point K where this length K to E is equal to AB. Are you guys able to follow me so far? Rehan, Shyam, everybody? So we are saying that okay, these two triangles we have drawn where ABC and DEF, where these two angles are matching and this side is matching, the side between the two angles are matching. So we are trying to find out if this side and this side are same or not. So we have gone to the assumption that they are not same. If the angle is same but the sides are not same, that's the assumption we made here. And if since this is not same, meaning one is bigger, one is smaller, so I'm saying okay, fine, let's say this side is bigger. So a point K on this line, when you join these two K and E, is equal to AB. So if you look at this triangle, meaning this KEF, the smaller triangle, and this ABC, what will happen here is that this angle, now this side AB is equal to this side KE. Okay, and then you saw that this side BC is equal to this side EF. Okay, so you got two sides matching and the angle between them also, angle ABC is equal to angle KEF. Okay, so between this triangle and this triangle we see that it is going by SAS. My two sides are matching, these two sides, and the angle between them is also matching. Both are 40 degrees. That means this small triangle, this one, after removing the green part of it, this KEF is congruent with ABC. But then this angle, this angle is not 60 degree anymore. This is less than 60 now. But this guy is 60 degree. So we are actually contradicting ourselves. Now Sonarka and Dhanusri are thinking, what is going on here? Correct? So see, there are two ways you can prove it. Right? This is a method of elimination, where you can say, okay, these two sides are same, and then everything falls in place. We are saying that, okay, let's assume that these are not same. If these are not same, then that means there is a smaller portion which is matching with this one, and then this smaller triangle is congruent with this guy. And if they are congruent, that means this angle and this angle are same, which is not the case. We are clearly seeing that. We picked a smaller length. We picked a small, we picked a point which is somewhere in the middle of this line. So we made this angle small. So we are saying that 60 degree is equal to something which is less than 60 degree. So we are contradicting ourselves, meaning the assumption that we made that this and this whole length are not same itself is wrong. That means they are same. They have to be the same. I know I took you guys for a ride. Let me take a pause here and gauge whether I was able to explain this to you guys or not. Did you guys understand what I did? Yeah, Nikhil.
So this essay three sides and the two sides and one angle and the two angles on one side, they're all congruent. But what about three angles are the same? Are they also congruent?
No. That is what is in my back pocket right now. I have not opened all my cards yet.
Okay.
Yeah. Yes, yeah.
So would CEF and ABC, would they be similar triangles then? It's like
No. No, we are not going to similar yet. Let's stay focused on congruence for now.
Okay.
So, see, what we are trying to do here first, let's try understanding that. We are trying to see this one. We saw that, okay, practically if you have three known sides, you cannot make anything other than two congruent triangles. Okay, that is one. Here we saw that if you have two known sides and then the angle is fixed, if the angle changes, your third side's length keeps increasing or decreasing. So the only way, if your angle remains the same, then the third side of the triangles will be the same, and they fall in this category, and so they are congruent. So this and this are congruent scenarios. Now we are looking at the third scenario, where it says that two triangles will be congruent if you have two matching angles and a matching side which is between the two angles. So to prove that, to reaffirm that this theorem is holding enough water, we are trying to check that. So we made two triangles where the base side is the same length and the two angles are also same length. And we said, okay, fine, these are same length, these two sides are same and these two angles are same, but this side and this side are not matching. That's what we assumed. And if these are not matching, meaning we assume that, okay, this side is probably bigger than AB. I mean, DE is bigger than AB. That means somewhere on the middle of, somewhere on this line, probably a point K makes this line KE same as AB. So if these two are same and these two sides are same, so when we looked at the smaller triangle after trimming the green part, this smaller triangle KEF became congruent with this guy. That means this angle, which is less than 60 now, because we trimmed one portion, right? So we took out this angle, right? Which I am shading right now. So we took little bit out of 60 degree. And we are saying that, okay, 60 is equal to something which is less than 60. That means the assumption that we made that this side and this side are not same was wrong. That eventually means they are actually the same. So now this side are same, this side are same, the angle between them are same. So ASA also relates back to SAS, and you can say, okay, yes, we can believe this theorem is also right. Don't go to similarity, okay? We are still talking about congruence. And we are just looking at the validity of all these theorems. Does it make sense? Nikhil, any doubt, beta? No?
No.
Okay. Rehan, are you clear? Dhanushri? Sunarka? Okay. Alright. So we saw that these three theorems, right? SSS, SAS, ASA, these three theorems we can believe hereafter. I mean, most of you believed these theorems before also, but since we reaffirmed that one more time, so now we have cleared some more dust. We should not have much doubt around this one anymore. Let's go to the next theorem, which is RHS. So this guy is like a stepchild in this group of theorems. Okay, what do I mean by that? These three theorems are for each and every type of triangles, any kind of triangle. If you're talking about isosceles triangle, equilateral triangle, scalene triangle, obtuse angle triangle, acute angle triangle, right angle triangle, these three theorems hold true for any type of triangle. Whereas this guy is very special. This guy says, I'm only talking about right angle triangle or right triangle. That's what R stands for. And then says, if there are two right angle triangles, where the hypotenuse and one of the side match, they are congruent. Meaning, if I have two right angle triangles like this, the hypotenuse are matching, and then one of the side, be it this side, or this side, or this side. So for right angle, say here we have three things to look at: two sides, one angle; three sides, two angles, one side. Here it says this just sets the boundary, saying that it is for right angle triangle. Where if you have two right angle triangles, if the hypotenuse and one of the side matches, then they are congruent. And I don't think we have to prove this one, because you guys have all learned about Pythagorean theorem. Excuse me if my spelling is not correct. Pythagorean theorem says that if this is A, this is B, and this is C, A square plus B square equal to C square. Here if you look at this, let's say this is hypotenuse is matching. So C is same. I'm saying this is A. And this is not B. This is let's say this is different from B. Not equal to B. This is what I'm saying. But that completely denies the Pythagorean theorem. Because your hypotenuse square is equal to this square plus this square. If this and this are same, this cannot be different from this guy. Yeah. So this is a reaffirmation exercise relating to Pythagorean theorem. Repeating it one more time, that if you have two right angle triangles where the hypotenuse and one of the sides match, then it will be they'll be congruent. Meaning, if your hypotenuse is already matching and one of the side is matching, then this side has to match. You don't have a choice, because in both the case, both are right angle triangle. So this square plus this square will be this square. This square plus this square will be this square. This and this are matching. These two are matching. By no means these two cannot match. That means your all three sides are matching. So it again relates back to this one, that your three sides are matching. Done. Yeah. Are you clear about this? Now let me tell you guys something which might sound funny, but it's very important. If I ever ask you guys to draw a triangle with sides 4, 3 and 8 centimeters each, can you draw it? Will you be able to draw it? If yes, please draw it. I'll give you $1 million. If you cannot draw it, tell me why. Yes, Pranit.
So in a triangle, if you're like taking a side, the one side, right, your base, the other two sides have added together, the length has to be greater than the base. In this, it cannot become like that.
Yeah.
Because 4 plus 3 is 7, and that's less than 8.
Yeah. So basically, I mean, the risk that I have of losing $1 million, that risk is gone. You cannot draw it, right? Nobody can draw it. Okay, sad. But good news is I did not have $1 million, so there is nothing that I'm losing. Okay, but this was just a concept where any triangle, if you look at it, you randomly pick any two sides. If you ever have the sum of the two sides greater than the third side, you are fine. But if any other combination, right? Here you have three sides, so you can look at 4 plus 3 as one combination, and the third one is 8. 8 plus 3 as second combination, the third one is 4. 8 plus 4 is your third combination, and the third one is 3. Third side is 3. If any of the combination is ever giving you not greater than this, you have a problem. This is not a legitimate dimension of a triangle, or this is not a dimension of a legitimate triangle, any which way. Okay? Why I am talking about this is primarily because there is a very strong bond or relationship between sides and the angles. Okay? Now if you look at things a little carefully, if I draw, so here this was just to show that okay, the sides have some relationship, and sum of any two combination of the sides has to be greater than the third side, the third remaining side. If you took these two, 4 plus 3 is not greater than 8, you're done. You cannot move forward and draw this triangle ever, no matter how much the bet is for. 8 plus 3 is greater than 4. This is a valid scenario. This is also a valid scenario, but this guy killed your chances of winning $1 million. Okay? Again, let me not talk about money, okay? Money is a very bad thing. Yep, yes, Aaron.
If like your sides are 4, 4, and 8, you could draw it, right? Because 4 plus 4 is equal to 8.
You will not be able to. It will not,
everything.
it has to be greater than 8. I'll tell you why. Because then it will not look like a triangle in the first place. See what will happen. Let's try drawing it here. This is 8 centimeters. Okay. Yep. Anil.
It becomes a line, right?
It becomes a line actually. So this is 4 centimeter and this is 4 centimeter. This is your bigger line, a line segment. This is the smaller side. One of the smaller side. This is the other smaller side. The only way it can look like a triangle is it has to be little more than 8. Little more than 8. And again, don't rely on my drawing skills. I'm saying even if it has to look like a triangle, it has to be like this. Then only you'll be able to believe that this looks like a triangle. And for that to happen, these two have to move a little bit up. And for this to move a little bit up, you will see that this line is a little bigger than this one. Yep?
Yeah, got it.
Okay. So, is everybody with me? Chris got tired of me and then rejoined again. Okay. Chris, Sarah, Dhanushri, everybody with me?
Yeah. Yes, sir.
Now let's look at one more interesting thing, which most of you would be knowing, but sometimes, with bare eyes, we tend to ignore. If you look at this triangle versus this triangle versus a very weird looking triangle. Okay. This one is a right angle triangle. This is an obtuse angle triangle, and this is probably a acute angle triangle. Assuming this is not 90 degree. Yes. Now, if you look at it carefully, just look at the visual part of it. There is no math involved here. You will notice that the sides which are opposite to the bigger angle are actually bigger. Meaning, if you look at this one, visually this looks the smallest of the three angles. This is little bigger than that, and this is the biggest of all. In this right angle triangle, this is your biggest angle, right? Now, which side is biggest? Obviously, the one which is right opposite to the biggest of all the angles. this side is smaller than this side because this angle is smaller than this angle. So what you are seeing here is smaller the angle is smaller will be the length of the side opposite to that. Same thing here also if you see. This angle looks biggest of the three, right? So that's why this side is probably the biggest. Visually, this angle is smaller. See, this side is certainly smaller than this. And this is the smallest angle, right? See, this side also looks smaller or smallest of the three that you see here. Go back to this triangle. See, this angle is the biggest of the three. That's why the side opposite to that is the biggest of all. Look at this angle, how tiny this looks. See what it did to the side opposite to that. Now this angle is obviously bigger than this one, looks thicker, and so is the side in the same proportion. So what I'm trying to say here is that in any triangle, the sides of the triangle are in proportion to how the angles are. If the angle is the biggest, relatively, okay? If this is the biggest angle, this side will be the biggest of the three angles. Biggest of the three sides that you see here. Does it make sense? Had you guys observed it before? Yep. Okay. Good. So now that concept will come handy for us. Chris, Sarah, Neil, Rehan, everybody okay? Sunarka?
Yes, sir.
Okay. Now this concept will come handy for us. Angle and the side opposite to that. That is where we'll talk about the photos, the zoom in, zoom out thing that we talked about, which is related to similarity. So all of you who were kind of excited to talk about similarity, and we were kind of trying to see a correlation between the congruence and similarity, this is where it is now. So as we talked, similarity is nothing but zoom in, zoom out. Yeah, we are zooming in, further zooming in. What doesn't change? Your angles. Again, extremely sorry for my poor, pathetic, disgusting drawing skills, but believe it to some extent. So when we are zooming in, zooming out, what is not changing for you is the angles. Your angles will remain the same. Only thing that changes are the sides. Your sides become bigger. Yeah. If you look at my picture and zoom in, it will look the next level of terror that you can think of by seeing anybody's face. But yeah, it just becomes bigger. Overall dimension, the relationship among the sides will not change. Relationship among the sides will not change. The ratio of the sides will not change. That's what I was trying to come to. Meaning, your angles are, let's say this is 1, this is 1, this is 1. This is 2, this is 2, this is 2. This is 3, this is 3, this is 3. Angles are remaining the same. What changes is the sides, and they change also in a proportion. Meaning, let's take a simple example so that we can represent this mathematically. So what similarity says is, when two triangles are similar, their sides will be in the same proportion. So let's say this is one triangle ABC, and this is smaller triangle DEF, which you got by you zoomed out and you got a smaller version. You zoomed in, you got a bigger version. That's the thing. So what it says is, your angles are same when you are zooming in, zooming out. So that means this angle and this angle are same. So let's say this is 1, this is 1. This is 2, this is 2. This is 3, and this is 3. I'm not saying this is a degree. I'm saying this is a third angle which has same value. So if 3 is 40 degree, both are 40 degrees. Okay, that's what I mean by that. So these are matching angles. Okay. So what similarity says is, if you have two triangles which are similar to each other, that means their sides will be in the same proportion. That means, now let's look at it. The only way you can relate two triangles as similar is based on the angles. So these are the two matching angles. So the sides, so I'm saying triangle ABC is similar to triangle, is this how you say similar? Or I'm missing something? This, okay, is triangle DEF. Yeah? If these two triangles are similar, meaning this angle are matching, this angle are matching, and this angle are matching. So their sides will be in the same proportion, meaning the sides appear to the matching angles. That's why I was stressing on that side angle relationship. Okay? So sides appear to the matching angle. Let's say on this side you have this angle and this angle on this side matching. So that means sides in the same proportion, meaning let's look at the sides appear to angle 1. What is the ratio? They are in what proportion? So that will be AC by DF. Both are the sides appear to angle 1 will be equal to, let's pick the second angle on the same triangle. Okay? Make sure that you don't jumble them up. Side appear to angle 2, which is AB, will be by side appear to angle 2, which is DE, will be equal to the third angle's sides. So third angle's opposite side is BC. Third angle's opposite side is EF. This is what it means. So if you have two triangles similar to each other, then their sides will be in the same proportion. Meaning if you have two triangles with matching angles, this matching, this matching, this matching, then the sides will be in the same proportion. Meaning, look at this. In the numerator, you have all the sides from one angle. In the denominator, you have all the sides from the other triangle. And then these are the sides appear to the same angle. So when you are picking up angle 1 and 1 here, you are putting this side by this side. When you are picking this angle similar, so you are putting this side by this side. When you are picking up these two angles, this side divided by this side. That is the ratio we are talking about. And this is based on the same understanding that your angles and the side appear to that have a relationship among themselves. And when you talk about similarity, this is the understanding that we have to have. Any questions with respect to whatever I have mentioned so far? Any questions? Sara, Sunarka, Sian, Neil, Praneet, Nikhil, Dhanushri, anybody? Chris?
No, sir.
No?
No, sir.
Everybody clear? 100% clear? 95% clear? You have to say a number. Thumbs up will not do.
100% clear.
100% clear? Wonderful. So, now, this concept is very important. If any of you get excited to relate to the Pythagorean theorem, right? I talked about that. Everybody in the world says, okay, Pythagorean theorem, a square plus b square equal to c square. Why? Pythagoras is just another person. Why would I believe him? Just because he has given me a theorem? No. We can always prove that. And Pythagorean theorem's core also lies in this concept. Okay? So, if you understand the similarity of triangles concepts, you can relate that to prove this. I'm not proving that right now. If anybody gets excited to figure it out, you have two options. You can say that, okay, sir, can you prove it in one of the class? I can do that. Or I can also share the link of the video where we have done that. Yes, share.
So Pythagorean theorem can be used for like any triangle and not only right?
Only right angle triangle or right triangle.
Okay.
So Pythagorean theorem, see, Pythagoras was such a small guy. He gave the theorem for this thing. But interestingly, Pythagoras, this cute looking triangle is not actually cute. I want you guys to sit down. We have still 3 more minutes. Settle down without making noise. Rudraksh, you had left your water bottle last time. Okay. Okay, give me 3 minutes so that I can wrap up what we are discussing right now. So, Pythagoras theorem is based on this concept called similarity, and we have proved that how it is derived, and that we can prove any time. What I don't remember is formulas. What I remember is the concept. So that's why whatever we talk about in the class, I try to keep it concept oriented so that you guys can always relate and prove if you want to. Okay. And to your point, Sriyan, what I was saying was this right angle triangle or a cute looking triangle is the mother of a completely new subject inside math called trigonometry that you guys would be knowing a little bit, and you would have explored that in the past, but we will come to that because that is going to be the next thing in the same unit. Okay, so this is just the tip of the iceberg. We are going to explore lots more when we go into this. Yep. So that brings us to the end of the class. We covered the theorem of congruence, how they came into existence, why should we believe that, why should we believe them, and we also saw how those are relevant to be believed. And then we'll look at the concepts around similarity, zoom in, zoom out, which you'll not forget, I believe, because I'm assuming that I've given you guys one of the most practical example that we deal with every day. Sit down. And then we look at what is the mathematical relevance of similarity, which we will use in the coming classes. So what we could not cover was the relationship of angles, but that is a topic that we can pick up tomorrow. And if there are more confusion, more doubts, more concepts around it, we will break our head with that, and I'll keep on scratching my head so that I keep on losing hair. Alright? With that being said, I will let you guys go unless you have any questions for me before you leave. Rehan, Sara, Neil, Shriyan, Sunarka, Praneet, Dhanushri, Dave. No questions? Chris? No questions? Okay. Then enjoy the rest of your evening, and I'll come back to bother you guys tomorrow same time. Yep. Alright. Bye bye. Take care.